Now, given that the state is ket alpha, the physical state is represented by ket alpha, okay, we do not know in advance into which of the various ket A prime the system will be thrown as a result of the measurement. Right? So we said that if you start with the state ket alpha, an arbitrary state ket alpha, and you measure an observable A, it will reduce to one of the eigenkets of this operator. It will reduce to one of the eigenkets of this operator. So let's say that there are eigenkets enumerated as ket A1, ket A2, ket A3, etc. Okay, so you have the state ket alpha. You are making a measurement of A. We know that it will change to one of these eigengets, but we don't know to which. It could change to this, it could change to this, it could change to this. All right, we don't know in advance exactly to which state it is going to change. All right, or exactly to which state, exactly to which eigenket it's going to jump. We don't know exactly to which eigenket it is going to jump, the state is going to jump as a result of the measurement of A. We know that it is going to be one of these eigengets immediately after measurement, but we don't know which in advance. Now, this is a little bit problematic, right? So what can a theory like this predict? The theory says that, all right, before measurement, it's in a superposition of all the eigengets. After measurement, it just jumps into one of these eigengets, all right? So such a theory doesn't predict much, all right? But there's something more that quantum mechanics says. There's a postulate which gives us the probability, okay, which gives us the probability that ket alpha will reduce to either ket A1 or ket A2 or ket A3. Right? So we have the quantum mechanics allows us to calculate the probabilities of these jumps, all right, or the probability for measuring certain eigenvalues. So when I say that the state has changed to ket A1, that also means that the measured value is A1, the eigenvalue. Okay, if it has changed to this, it also means that the measured value is A2. If it has changed to A3, ket A3, that also means that the measured value is the corresponding eigenvalue. All right. So quantum mechanics tells us what's the probability for measuring a particular eigenvalue. All right. For example, let's say that the probability for measuring a eigenvalue A prime. Quantum mechanics says that this is given by modulus square of bracket A prime alpha. Okay, what is this? This is the component of ket alpha in the direction ket A prime. This is the component of ket alpha in the direction ket A prime. Okay, for example, so this is the postulate that gives us the probability for different measurement outcomes. Okay, so quantum mechanics allows us to calculate these probabilities by this postulate. Okay, let me elaborate a little bit on this because this is very important, right? So let's try to make things clearer. Let's say that ket alpha is in this particular superposition. For example, C1 ket A1 plus C2 ket A2 plus C3 ket A3, etc. Okay, there could be other things. Okay, so this postulate says that the probability that ket alpha will change, let me write it like this, all right? The probability that ket alpha will change to ket A1, all right, after a measurement of A, the probability that this change will happen is given by the modulus square of this expansion coefficient. This is equal to modulus C1 square, all right? Similarly, the probability that the initial ket will change to A2, this is given by modulus C2 square, the corresponding expansion coefficient here. Okay, the corresponding expansion coefficient here determines the probabilities. These expansion coefficients determine the probabilities. Okay. Now we know that modulus of C1 square can also be written as C1 is the component of ket alpha in the direction A1. So that's C1. So modulus square, you have to modulus square this. Okay. So similarly, modulus of C2 square is, what is C2? It's the component of ket alpha in the direction A2. So modulus C2 square is bra A2 ket alpha modulus square of bra A2 ket alpha. All right. Now this also can be written in this form. So when I say that ket alpha has changed to ket A prime, that means that I have measured a value A prime or A1. All right. That means that I have measured an eigenvalue A1. So you can also say that the probability for measuring an eigenvalue A1 or measuring A1 is equal to modulus of C1 square or modulus square of bracket A1 alpha, bracket A1 alpha. Okay. So these two things are the same thing. All right. I could either say the probability that the state changes from ket alpha to ket A1, or I can say the probability of measuring the eigenvalue A1. Okay. Now, if you are asked to find the probability for measuring a particular eigenvalue, what would you do? Right. Suppose you are given a state ket alpha. Suppose you are given a state ket alpha, and you are asked the question, what's the probability that you will measure a particular eigenvalue A3 of the observable A? That's the question. The question is, given the state ket alpha, what is the probability that you will measure an eigenvalue A3 for this observable A? All right, or what's the probability that you will measure? You will get as a measurement outcome, you will get A3. Okay, if you measure the observable A. To find this answer, you first have to take the corresponding eigenket, right? You have to take the eigenvalue, you have to take the eigenket corresponding to this number, and that eigenket is denoted as ket A3. All right. Now what you do is that you take this state and project this state onto this eigenket corresponding to this eigenvalue. Okay. So take the eigenket corresponding to this eigenvalue and project the given state onto that eigenket. We are not done. You'll get a complex number if you do this. This you can also call as C3. Now you have to take the modulus square of this. This could be a complex number. Okay, this is a complex number in general, but if you take the modulus square, you get a real positive number. This will give you the probability for measuring an eigenvalue A3. Okay, or for getting A3 as a measurement outcome. This is the probability for obtaining A3 as a measurement outcome. All right. Now this is true. This rule is true if ket alpha is actually normalized. This means that ket alpha bracket alpha alpha is equal to 1. Now this rule is true. This equality holds true only if ket alpha is normalized. Okay, we'll see this in more detail. Right. If ket alpha is not normalized, then you have to replace this equal sign by a proportionality sign. That's all. Right. If this is not normalized, this would be a proportionality. If it is normalized, then this is an equality. All right. So we see that this normalization condition that we used, right, the reason why we use normalized kets in quantum mechanics is that it has to do with the probability interpretation. It has to do with the calculation of probabilities. All right. This is the reason why we actually use unit vectors. All right. Or we prefer unit vectors to represent physical states or quantum mechanical states. Okay. So instead of kets of any length, we'll use we'll use what is a unit vectors in a sense. All right. So that this probability can be calculated easily. All right. Now, what happens if the given ket is not normalized? All right. Suppose you have a ket alpha tilde, and suppose that this is not normalized. Suppose this is not normalized. All right. The inner product is not equal to 1. Then what we do is that we will normalize this state. We will normalize the state first. Once we normalize the state, you can use the same rule to calculate the probability. You can use an equality sign. How do you normalize? How do you normalize this? You divide ket alpha by bracket alpha tilde alpha tilde. Actually, the square root of this. Right? This will normalize the state. Right? We have already seen that this will normalize the state. Okay? Now, this new state we can call as ket alpha. Now, in this ket alpha, you can use this rule. Right? So, in order to use this rule, you have to first normalize the given state. Okay. Now, we so far talked about a single physical system. All right, we talked about a single physical system represented by the ket alpha. All right, and what's the probability for measuring a particular eigenvalue, a particular value A prime of an operator A. Okay, so we talked about a single physical system represented by ket alpha, and we asked the question, if I measure an observable A on this ket or on this state, what's the probability that I'll get a value A prime, for example? Right, and we gave the result for this. All right. But how do we calculate it empirically? All right. How do we measure this probability empirically? So we know that in order to find the probability empirically, you need a large number of measurements. Okay, but we cannot do it directly, because if I take ket alpha, state ket alpha, and make a measurement of A, what happens? This changes into one of the eigenkets of operator A. All right. So I cannot. So the state has changed. The state has changed. All right. So making repeated measurement doesn't mean much here. So what I need to do is that I'll have to take many systems all in the state ket alpha. So I make a measurement on this, okay, and then discard it, all right, because now the state has changed. Okay? Then I take the second system, which also is represented by exactly the same ket, and then I make the measurement on this ket, all right. Then I discard it, all right. Then I take the next system, which also is represented by the same ket, and then I make the measurement of observable A. All right. Then suppose I get n1 times the value a1. Suppose I get n1 times the value a1, n2 times the value a2, etc. And suppose we have made a large number of measurements given by capital N, right? Then we can say that the probability of measuring a1, this is something that we are calculating empirically, all right, is n1 divided by capital N. That is the fraction of times you get the value a1. That's the definition for probability. Okay, so P of A1 is the number of times you measured the value A1 divided by the total number of measurements, so the total number of identical systems that you prepared. Now, ideally, this has to be a large number, right? So, in order to calculate the probability empirically, you need a large number of systems, all right, or you need a large number of measurements. Okay, all right. So, this is how we calculate the probability empirically. Okay. So, to determine probability empirically, we must consider a great number of measurements performed on an ensemble, that is, a collection of identically prepared physical systems, all characterized by the same ket alpha. All right. Now, such an ensemble is known as a pure ensemble. Okay, such an ensemble is known as a pure ensemble. What do we mean by pure ensemble? If it's an ensemble of systems all characterized by exactly the same ket, then we say that it's a pure ensemble. Okay. Now, as an example, you can think about a beam of silver atoms. For example, how do I construct a pure ensemble? All right. So what I do is that initially I don't know anything about the spin. So what I do is that I send this. I send these atoms into an SGZ hat apparatus. All right. Now we know that there are two possible outputs. Okay, there could be an output corresponding to state characterized by state Sz plus, and there could be another output characterized by state Sz minus. Okay, then I block this. Right, then I block this. I block the all atoms which are characterized by Sz minus. All right. So I have only one output here, and all the atoms coming here are now characterized by exactly the same state. All the atoms here will have the same state represented by Sz plus. Now you can call this as a pure ensemble. Okay. All right. So we have talked about this measurement and probabilities. So we see that these probabilities enter into quantum mechanics in a very fundamental manner. Okay, it's because of superposition that we need this probability. And if superposition is a fundamental fact of nature, fundamental fact of the world, then that means that this probability type of description cannot be avoided. All right. Now you can compare this with the case of probabilities in classical mechanics. So in classical mechanics also we use probabilities. For classical systems also we use probabilities. But when do we use probabilities? We use probabilities when the complete information is not available. Right? When the complete information is not available. For example, in classical statistical mechanics, we use the language of probabilities all the time. Okay? You could even think of the case of tossing a coin. Right? So we usually say that if you toss a coin, you will get a head. Okay, the probability for getting head is half, and the probability of getting tails is half. Right? We say that these are equal probabilities. And how do we measure this experimentally? You make a large number of measurements. Suppose you get n1 heads. Okay, n1 by capital N, the number of measurements will approximately be equal to half. all right? And this equality, this approximation will become more and more better if capital N becomes larger and larger. Okay, so this is the empirically measured probability. So we say that the probability is half, but why do we use the probability language here? It's because we don't have all the variables that affects the coin toss, all right? Now suppose you knew everything about all the forces acting on the coin, the pressure around. If you know all of these things, in principle, we could predict with certainty whether it's going to be a head or a tail. If you know how much force, how much torque you are giving, or how much force you are giving, and you know the air pressure and all the relevant variables, in principle, the calculation may be very complicated, but in principle, we can know with certainty whether it's going to be a head or a tail. Okay, so in classical situations, we use the language of probabilities only because we don't know all the variables. We don't know all the variables that affects the system. We don't have sufficient information. All right. So in classical mechanics, the reason why we use probability is because lack of information. Lack of information. Right? But in quantum mechanics, the situation is different. Right? So if you get enough information, you don't need the language of probability in classical mechanics. In quantum mechanics, the situation is different. Okay, I think we postulated that everything that you can know about the system is contained in this ket. So if you have given the ket, you know all the information regarding the system. Okay, there is no lack of information. The ket represents all the information. It includes all the information that you can actually gain about a quantum mechanical system. So we know all the information. We know the exact state of the physical system. But even if you know the exact state of the physical system, we don't know the outcome of the measurement. We don't know the outcome of various measurements. In classical mechanics, if you know the state, you know the outcome of the measurements. These are the same things. In quantum mechanics, there's a deep difference between states and observables. All right, you could know the state of the system in all the possible details, but this does not give you the knowledge, what do you say, perfect knowledge about measurement outcomes. It only gives you the knowledge of, let me put it like this, knowledge of the state, or perfect knowledge. Let's say perfect knowledge of the state does not guarantee perfect knowledge of measurement outcomes. So perfect knowledge of the state does not guarantee perfect knowledge of measurement outcomes. All right. Even if you have perfect knowledge of the state, all right, you only know the probabilities for various measurement outcomes. You only know the probabilities for various measurement outcomes. Okay. So we see that probability is what do you say? It enters quantum mechanics in a very fundamental manner. Okay. So these probabilities, this probability description cannot be avoided by collecting more information of the system. Right? You cannot simply avoid these probabilities by collecting more information. This is there in a very fundamental manner. So you have to understand that these probabilities that we are talking about in quantum mechanics are quite different from the probabilities that we talk about in classical mechanics. Okay, of course you will have quantum statistical mechanics. In that case, you may not know the state of the system exactly. All right, in that case, you may have to introduce probabilities just like we do in classical mechanics. All right, but still there is a deeper layer of probabilities which exists even if you know the state in all its details. Okay, so this is something that makes quantum mechanics different. Perfect knowledge of the state does not guarantee perfect knowledge of measurement outcomes. Okay, perfect knowledge of the state will give you perfect knowledge of probabilities for various outcomes. Okay, so this is what is happening. Now the probabilistic interpretation for the squared inner product of this form, all right, this should be thought of as a fundamental postulate of quantum mechanics. All right, this is a fundamental postulate of quantum mechanics. The idea that these inner products, the modulus squared of these inner products, are related to probabilities. All right, this is a fundamental postulate of quantum mechanics. So when I say it's a fundamental postulate of quantum mechanics, it means that it cannot be proven from more basic principles. Okay. All right. Now let's note that it makes good sense in extreme cases. Let's look at an extreme case. Right? Suppose the state is given by get A prime. It's one of the eigenkets of operator A or observable A. Okay. Now, if I measure A on this state, I know that I am going to get the corresponding eigenvalue A prime. Okay, which means that you are sure that you are going to get the eigenvalue A prime. This means that the probability for measuring A prime has to be equal to 1. And it makes sense because according to this postulate, the probability for measuring A prime, how do you calculate the probability for measuring A prime? You take the corresponding ket, the corresponding eigenket, right? The eigenket corresponding to this eigenvalue, which is ket A prime, and you project the given state onto this state, all right, or onto this direction. Okay, so you take the given ket, which is ket A prime, project it onto ket A prime, and take the modulus square. And by orthonormality, right, we know that this is 1 because this is equal to 1. All right. So suppose the state ket is ket A prime itself, even before a measurement is made, then according to our probability interpretation, all right, the probability for getting A prime, or more precisely, for being thrown into ket A prime as a result of measurement is predicted to be 1, which is just what we expect, right? We said that we expect it to be 1. If the state is ket A prime, we expect the measurement outcome to be eigenvalue, the corresponding eigenvalue, which is A prime. And the probability for getting this eigenvalue is 1 because there is no superposition here. There is no superposition in terms of eigenkets of observable A. Right? So if it is, so the idea is that if you want to make a measurement of an observable A, all right, on an eigenket of this observable, then you are sure to get the eigenvalue A prime as a measurement outcome. All right. Now, if you are making a measurement of A on a superposition of these eigenkets, because these are also possible states in quantum mechanics, all right? These are also possible states in quantum mechanics. So, if you want to make a measurement of the observable A in a state which is a superposition of these eigenkets, then we will get one of the eigenvalues and which we don't know which. And quantum mechanics will give us the probability for getting each of the eigenvalue. All right. So we can say that if it's in an eigenket, you are sure to get the eigenvalue A prime. In other words, the probability is 1. And this is also the idea that the probability is 1 is also shown from this postulate. Right? The probability can be calculated like this, and clearly this is also equal to 1. Right? So this rule, this postulate actually makes sense in this particular extreme case. Okay. This means that you are not going to get any other eigenvalue of A. If the state is ket A prime, you are not going to get any other eigenvalue of this observable. You are only going to get this particular eigenvalue. The probability for obtaining all other eigenvalues is 0. Okay. Now, by measuring A once again, we of course get A prime only. Right? So let's start with the state ket alpha, which is in a superposition of all the eigenkets of operator A. Right? Now I measure the observable A on the state. Let's say that the state has changed to ket A prime. Right now I can calculate the probability for getting ket A prime as bracket A prime alpha modulus square. Right? So we know we can do that. Right? The next question is, I repeat the measurement of A. Right, on the same system. I measured A once. Let's say that I got an eigenvalue A prime. So state is the corresponding state after measurement is ket A prime. Right. If I repeat the measurement A, I am sure to get the eigenvalue A prime. Okay, which means that the state continues to be in ket A prime. Okay. So the measurement doesn't. We said that if the system is in an eigenket of observable A, then the measurement of observable A does not change the state. All right, we said this earlier. Okay. So that's what we say here. By measuring A once again, we of course get A prime only. Quite generally, repeated measurements of the same observable in succession yield the same result. Right. So if I repeat the measurement of A on this state, okay, I'm repeating the measurements, then I'm sure to get the same value. The value won't change. Right? But the only condition is that you have to repeat the measurements in quick succession. You shouldn't wait for a long time. Okay, so the repeated measurement has to be done immediately after. The reason is that these kets evolve with time. Right? So according to a dynamical law called Schrodinger equation. In the next chapter, right, we'll talk about quantum dynamics, and there we'll see that if you wait for a long time, there's a chance that this ket will evolve into a superposition again. So now it's not in a superposition with respect to the eigenkets of A, but if you wait for some time, it may evolve into a superposition of the eigenkets of A. All right. So and then this statement is no longer true. Then this statement is no longer true. Okay. If on the other hand we are interested in the probability for the system initially characterized by ket A prime to be thrown into some other eigenket ket A double prime with A double prime not equal to A prime, okay, then our result gives 0 because the orthogonality between A prime and A double prime. So this is what we are saying. Suppose you start with the state ket A prime, all right, and you are making a measurement A. The question is, what's the probability that you'll measure a value A double prime which is not equal to A prime? What's the probability that you'll measure A double prime which is not equal to A prime? So in the previous slide, we said that the probability for measuring A prime, if this is the state, the probability for measuring A prime is actually 1. Right? We are sure that you are going to get this eigenvalue. This also means that the probability for getting any other result is 0. Okay, any other result or any result other than A prime is 0. You are going to get the eigenvalue corresponding to this eigenket. This is for sure. Okay, so this means that the probability for A prime has to be equal to 0. Because we said that the probability for A prime is 1 and the total probability, the probability of all the possibilities should add up to 1, right? Okay. We can also see this from here. The rule for calculating the probability for measuring A double prime is to take the eigenket corresponding to this eigenvalue. You want to measure the probability of measuring A double prime. So you take the eigenket corresponding to this eigenvalue. Okay, we'll denote it as ket A double prime. Now you project this initial state onto this ket. Okay, how do you project? You take the initial ket, project it onto this ket, all right, and then take the modulus square. But by orthogonality, all right, these are eigenkets corresponding to different eigenvalues. They are orthogonal. So this is equal to 0. So this is equal to 0 as expected. Okay. Now, from the point of view of measurement theory, orthogonal kets correspond to mutually exclusive alternatives. Right? Orthogonal kets correspond to mutually exclusive or alternatives. So when we say that two kets are orthogonal, right, they correspond to mutually exclusive outcomes. Right? For example, if you say that the system, spin half system is in the state ket Az plus, then we are sure that if you make a measurement of Sz on this, you are sure that you are not going to get minus h bar by 2. You are sure to get plus h bar by 2 and you are sure not to get minus h bar by 2. Okay. So when you say that you are sure not to get minus h bar by 2 on a measurement of Sz on this state, right? So this can also be said as, if the probability for measuring minus h bar by 2 is 0, you can say that these are actually orthogonal states or orthogonal kets. Okay, so we can say that the component, this means that the component of Sz plus in the direction Sz minus is actually 0. Okay, so if it's in the state Sz plus, you are not going to measure minus h bar by 2 for the z component of spin. These are mutually orthogonal or mutually exclusive. Or if it's in the state Sz minus, and if you are measuring Sz, you are always going to get plus h bar by 2. Sorry, minus h bar by 2. You are never going to get plus h bar by 2. Okay, there's no possibility for that. There's no probability for that. The probability is 0. Right? So we can say that if a spin half system is in the state ket Sz plus, we know for sure that it cannot be in the state Sz minus after a measurement. Right? This we know with certainty. This we know with certainty. Okay. So what we saw here is that the probability for measuring a particular eigenvalue is obtained by this rule. Okay. If you start with the state ket alpha, the probability for measuring a particular eigenvalue A prime of the observable A, right, is this. This is the postulate. Right. Now the probability for anything must be non-negative, and clearly this is non-negative because this modulus square of a complex number. This modulus square of a complex number. This is of the form z star z. Right. So if z is equal to a plus ib, okay, Z star is equal to A minus IB Z star or modulus Z square. Okay, this is equal to A square plus B square. This is the sum of squares. So this is clearly positive. It cannot be negative. Okay, and we know that probabilities cannot be negative. Right? Probabilities cannot be negative. So our postulate is consistent with this rule. Quite generally, the probability for anything must be non-negative, and this is met with our probability postulate. Right? Furthermore, the probabilities for the various alternative possibilities must add up to unity. This is also true. If you have two possibilities, for example, if you are tossing a coin and you have two possibilities, all right, you have the probability for getting head and you have a probability for getting tail. All right. So if the probability for getting head is 1 by 2, then the probability for getting tail has to be not minus 1 by 2. It also has to be 1 by 2. And they have to add up to 1. They have to add up to 1. So if there are only two possibilities, and if you know the probability for one possibility, the probability for other possibility can be found by subtracting the probability for the first possibility from 1. Okay, I think we already know this thing. So here also we see that the probability for getting head plus the probability for getting tail has to be equal to 1. All right. Or we can say the probability of getting head or tail. Okay, this is equal to 1. This means that you are guaranteed to get either head or a tail. You are guaranteed to get either head or a tail if these are the only possibilities. Okay. So the probabilities for the various alternative possibilities must add up to unity. All right. Now this expectation is also met by the the postulate that we saw just before. Okay, what was the postulate? The probability can be calculated by this thing. All right, P of A prime is equal to bra A prime get alpha square modulus square of this quantity. Okay. Now this is the postulate, and this postulate also is consistent with the fact that the probabilities for various possibilities must add up to unity. So we can actually check this. We said that this rule is true. This equality holds true only if the state alpha is normalized, or where the state alpha is normalized. So state alpha normalized means bracket alpha is equal to 1. Okay. So let's check that thing. All right. We start with the idea that the state is normalized. So bracket alpha is equal to 1. All right. Now again, as usual, let's introduce an identity in here. Let's write this as the identity operator as 1 is equal to sum over A prime get A prime bra A prime. Let's insert it here. So this means that bra alpha, I'll put this summation over A prime here. Okay. Get A prime bra A prime get alpha, this is equal to 1. This means that sum over A prime, okay, this can be written as bra A prime get alpha star, all right, because of this basic rule that we had. Bracket alpha beta is equal to bracket beta alpha star. Okay, so using that, I can write this first term as bra A prime get alpha star, and this can be written as bra A prime get alpha. So this is a number, this is another number. So you are multiplying a number by its complex conjugate. Okay, this means that sum over A prime modulus square of bra A prime get alpha square, modulus square of bra A prime get alpha is equal to 1. Sum over all possibilities. All right, these are A prime. Sum over A prime is the sum over all possibilities. Right, so we see that the sum over all possibilities add up to 1. All right, so the condition for the normalization of the state is actually the condition that the probability for all possibilities, all alternatives add up to 1. I repeat, the condition for normalization, the condition that the state is normalized is equivalent to the condition that the probability over all possibilities add up to 1. Okay, so both these expectations are met by our probability postulate. Right? So the expectations are that probabilities must be non-negative. That is true. All the probabilities of various possibilities will add up to 1. This is also true, as we have shown here. Right? Because we had specifically said that the probability is equal to the probability for a prime is equal to a bracket a prime alpha modulus square only if this condition is satisfied, only if the state is normalized. Okay, so state being normalized means that the probabilities will add up to 1. Okay. Now perhaps you also understand why we had the postulate of a positive definite metric. Okay, we postulated that the metric is positive definite, or the inner product of a vector with itself. In a sense, this is greater than or equal to 0. All right. Why did we have this? Because this is understood as a sum of probabilities, and this has to be positive. Right? This has to be greater than or equal to 0. If it's normalized, it's 1, or it has to be greater than, it could be greater than 1. In that case, we have to normalize it. All right. So anyway, this condition is important for the probability interpretation. All right, as we had mentioned earlier. Expectation values of observables. We define the expectation value of an observable A taken with respect to a state ket alpha as, okay, expectation value of A is equal to, or this is defined as bra alpha A ket alpha. This is a number. This number is called the expectation value. All right. To make sure that we are referring to the state ket alpha, the notation like this is used. All right. So we use this notation expectation value in the state alpha. You can read this as expectation value of A in the state alpha, in the state ket alpha. All right. Because if you change the state, all right, in a different state, the expectation value of A also could be different. So if you want to specify the state, we can denote it like this. All right. Now, what does this expectation value actually mean? Let's try to understand what this expectation value actually means. So let's look at this expression. I've got bra alpha A ket alpha. All right. Now, again, as usual, we can introduce the identity operator here and here. Right. So let's introduce the identity operator like this: sum over A double prime, sum over A prime. Okay. I have got this bra alpha ket A double prime, bra A double prime. Okay, so summation over A double prime, ket A double prime, bra A double prime is an identity. Okay, it's an identity operator. And then I have this A here. Then I introduce the next identity here. Sum over A prime, ket A prime, bra A prime is again an identity operator. So I have just multiplied by 1 on both sides of this operator A. And I have got this alpha here. All right. Now we know that this A, all right, this ket A are the eigenkets of operator A. All right, so this means that A acting on ket A prime is A prime multiplied by ket A prime. This means that ket A prime is an eigenket of operator A corresponding to the eigenvalue A prime. Okay. This means that this can be written as A prime ket A prime. Okay, A acting on ket A prime is given by A prime multiplied by ket A prime. So let's write that step here. This is equal to sum over A double prime, sum over A prime. I have this alpha. This is bra alpha ket A double prime. And this I can write now as bra A double prime A prime ket A prime. Then I have this bra A prime ket alpha here. Okay. Now what is this? This is a number. All right. The number can be pulled out because it doesn't matter where you write the number. All right. It doesn't matter whether you write it on the right side or on the left side of a ket or a bra. So you can pull this number out. So this becomes sum over A double prime, sum over A prime. Let me write this number here, A prime. Okay. And the rest of it I have bra alpha ket A double prime. And what is this? This is bracket of A double prime A prime. These are eigenkets of operator A. Okay. So we know that this is from an orthonormal set, and bracket A double prime A prime is actually delta A double prime A prime. Okay. And I also have this bra A prime alpha here, ket alpha here. All right. Now there are two summations here. I can carry out one of the summations. All right. Let's carry out the summation over A double prime. Let's first carry out the summation over A double prime. So what happens when I carry out the summation over A double prime? Here we see that we have a term delta A double prime A prime. When I carry out the summation over A double prime, there's only one non-zero term. Right? In the whole summation, there's only one non-zero term, and that term corresponds to A double prime equal to A prime. Okay. So if I carry out this summation over A double prime, this Kronecker delta, this is the Kronecker delta. It says that if a double prime is equal to a prime, this is equal to 1, and if a double prime is not equal to a prime, this is equal to 0. Alright, this means that the only non-zero term in the summation over a double prime is that for which a double prime is equal to a prime. So I can carry out this summation, and then the Kronecker delta will disappear, and wherever there's a double prime, it will become an a prime. Okay, that's the action of the Kronecker delta and the summation. We know that. You can think of it as the definition of the Kronecker delta. Okay, so let me write it here. This becomes, I have carried out the sum over a double prime. Right? So this becomes sum over a double prime. I've got an a prime here. This is bra alpha. This is get a double prime. But when I carried out the summation over a double prime, this means that I have to sum over all possible values of a double prime. Right? When you sum over all possible values of a double prime, in that summation there will be one term corresponding to a double prime equal to a prime, and that's the only non-zero term. Right? So that means that this is the only non-zero term corresponds to a double prime equal to a prime. Okay. Again, the non-zero term corresponds to a double prime equal to a prime. Then delta is 1, and I have got this bra a prime get alpha. Okay, bra a prime get alpha. Now I can write this as sum over a prime bra a prime get alpha star bra a prime get alpha, right? Because we know this rule, bra beta get alpha, or bracket beta alpha is equal to bracket alpha beta star. I have just used that rule here. Okay, now this becomes sum over a prime modulus, this is a complex number multiplied by its complex conjugate, so it's modulus square of bracket a prime alpha. What was this? This we postulated is the probability for measuring the eigenvalue a prime. This is the probability for measuring the eigenvalue a prime. Am I right? So I can write this definition. So I have started with this definition of expectation value, and I see that it reduces to this expression. This is the sum over a prime. What is this? This is the probability of a prime. Probability of a prime multiplied by a prime. Okay. So you see that it's a weighted sum of the eigenvalues. Right? What we mean by an expectation value is actually a weighted sum of the eigenvalues. So each eigenvalue is weighted by its probability. Right? Now this is exactly what we call an average value. This is exactly what we call an average value. Right? So this means that I shall show that this is exactly what we call an average value. This means that expectation value actually means average value. Expectation value actually means average value. Okay. So the question is, if I make a large number of measurements on identically prepared systems, right? If I make measurements on identically prepared systems for a particular observable A, you can ask the question, what's the average value of the measurement outcomes, and the result that can be predicted in this form. What's the average value in the state get alpha? It can be obtained by bra alpha A get alpha. All right. Now let me just explain why this is the average value. Right? What do we mean by an average value? Suppose this is the theoretical calculation that we have done. Suppose you make a measurement. And suppose you have a large number of identically prepared systems. You have a large number of identically prepared systems. You measure A on this system and you discard this. Right? You measure A on this system again, and then you discard that also because the state has changed. In this way, you measure the observable A on each of these identically prepared systems. Right? Now let's say that n1 times I obtain a value A1. Right? And n2 times I obtain a value A2. We need a large number of identically prepared systems like this, and n1 times I get a value A1, n2 times I get a value A2, n3 times I get a value A3, etc. Right? Now what's the average value? You might have calculated average values in your laboratory, etc. The average value is n1 A1 plus n2 A2, which means that you are adding up all your results. All right, you are adding up all your results, and you are dividing it by the total number of systems or the total number of experiments. Okay, this you can write as n1 plus n2 plus n3, etc. Okay, all right. So I have got, if I do measurements on identically prepared systems, I'm getting n1 times a1, n2 times a2, etc. I add up all these results. Okay, a1 a1 plus a1 plus a1 like that n1 times. So we write n1 a1 plus n2 a2 plus n3 a3. Right. Now this n1 plus n2 plus n3 is the total number of measurements or the total number of experiments that you have carried out. I can write it as capital N. Right. Now I can write this as, this is the average value. Right. This is the average. Let's say this is the average A. This is the definition for average A. Now I can write this as, n1 divided by n multiplied by a1 plus n2 divided by n multiplied by a2 plus n3 divided by capital N multiplied by a3, etc. Right. Now what is this? This is the fraction of times I obtained a value a1. This is the fraction of times I obtained a value a2. This is the fraction of times I obtained a value a3, etc. Okay, and this fraction of times you obtain the value a1, this is exactly what you call as the probability, the measured probability for the measured probability, or yeah, the empirically measured probability for obtaining a1. So I can write this as, let me write it here, this can be written as probability p1 a1 plus p2 a2 plus p3 a3, etc. Right. So what is this? This is the weighted sum of all the results. What do I weight with? I weight it with the fraction of times I got this particular result. And this is exactly what I call the probability. Okay, so I started with the expression for average value, and I see that we can write it in terms of the weighted sum of the results. All right, that's exactly what we have here. That's exactly what we have here. All right, this is why we say that by expectation value we mean actually average value. All right, so it may be a bit misleading. Sometimes you may think it's the expected value of a measurement. No, it's not. All right, so expected value of what's the expected value of a measurement? If you make a measurement, the expected value, what value do you expect? The expected value may be the most probable value. All right, what's the most probable measurement outcome? That may be the expected value. Right, but by expectation values we mean the average of all the measurement outcomes. Right? So this is the theoretically predicted average value, and this is how we'll experimentally calculate it. This is how we'll experimentally calculate it. Okay. So that is, uh, so we have seen what we mean by expectation values of observables in quantum mechanics. Now we know how to calculate these expectation values. Okay. All right. So the definition, expectation value of A is equal to, in the state alpha is equal to bar alpha A get alpha. Right, this agrees with our intuitive notion of average measured value. Right, because it can be written like this. You will see that, so this A prime should appear here, sum over A prime multiplied by the probability. This is exactly the average measured value, and that's what we calculate by this expression. Right, now since we are just beginning with this subject, it's important not to confuse eigenvalues with expectation values. For example, the expectation value of Sz for spin half systems can assume any real value between minus h bar by 2 and plus h bar by 2. Okay, for example, it could be 0.273 h bar. The average value could be 0.273 h bar. Okay. In contrast, the eigenvalue of Sz, if you are talking about the eigenvalue, it can have only two values. It's either h bar by 2 or minus h bar by 2, never in between. But the average value could be in between h bar by 2 and minus h bar by 2. It could be 0. For example, if you are making a large number of measurements and you get equal number of times, you get, let's say, n1 times h bar by 2 and again n1 times minus h bar by 2. If you get plus h bar by 2 and minus h bar by 2 an equal number of times, then the average value is just 0. Then the average value is 0. Right? So uh, don't confuse between, or don't mistake between eigenvalues and expectation values. All right. So with that, we'll conclude our discussion on probabilities and expectation values. Thank you. Let me just summarize what we have learned so far. We talked about the measurement process, and we said that in quantum mechanics, the measurement of an observable A on a state get alpha, all right, results in a change of state into one of the eigengets of observable A. So if I start with the state get alpha, measure the observable A on it, okay, the state changes to one of the eigengets of this operator. All right, and usually a measurement is accompanied by a change of state. But there is an exception. If you are starting with an eigenket of A itself, if you are starting with an eigenket of A itself, then there is no change in state. Then there is no change in state. All right. And again, if the state changes from ket alpha to ket A prime, then we say that the measured value is the corresponding eigenvalue A prime. Okay. In this case, we are certain to get the in this case, all right, we are certain to get the eigenvalue A prime, but in this case, we don't know. Before measurement, we don't know which of the eigenvalues of A we are going to get. We are sure to get one of the eigenvalues of A, but we don't know which. All right. Okay. Now, quantum mechanics gives us a rule or a postulate to calculate the probabilities. The probability for measuring a particular eigenvalue A prime can be found like this. All right. You project the given state, the starting state, onto the eigenket corresponding to this eigenvalue and take the modulus square. This will give you the probability, provided this state is normalized. Provided this state is normalized. Okay. So this is the rule for finding the probabilities. We got the rule for finding the expectation value. Okay, we defined the expectation value like this. Expectation value of A is equal to bra alpha A ket alpha. All right, and we saw that this is actually the average value. This is actually the average value, sum over A prime, P of A prime multiplied by A prime, which is the definition for average value. Okay, so these are some of the things that these are the important things that we discussed in the previous two sessions. Okay.